Hi, and welcome to C.4 Standing Waves. Now, I personally, sadly, was not blessed with a music gene within me. In fact, as I was learning the saxophone at high school, I think it was actually torture for my parents, I'm not going to lie. But any of those who have an interest in music, this is where the fundamentals of wind instruments lie. Standing waves. And it's a super interesting topic, so I hope you enjoy it. Let's start by finding out what a standing wave actually is and the conditions necessary for their formation. And we'll also look at phase difference and superposition, which we studied in previous topics, and we'll find out how they relate to standing waves. But first, actual examiner feedback for standing waves. The examiner expressed surprise at the number of candidates who had difficulties with the basic explanation of the formation of standing waves. So let's get straight on to that. Standing waves. Two waves of the same frequency and amplitude. So we have a wave here and a wave there. You can see that they have the same wavelength and frequency, and they have the same amplitude. Will form a standing wave if they superimpose when travelling in the opposite direction. So if the waves have the same frequency and amplitude and are travelling in the opposite direction, we can see that they form a standing wave like this. Standing waves have particular characteristics that we should be aware of. They have nodes, and I'm pointing to the nodes here. These are points where there is total destructive interference and no displacement of the particles within the wave. We also have antinodes, the opposite of nodes, and these are at the maximum points. This is where total constructive interference has taken place between the two waves, and there is a maximum displacement of the particle within the wave. When we think about a progressive wave, we think about it transferring energy. The main difference between a progressive wave and a standing wave is that a standing wave does not transfer energy. The previous slide showed a still of what a standing wave looked like, and this animation on this slide shows how they're formed. You can see there's a blue wave and a red wave in the background, and they're superimposing onto each other to create this black pattern as we see it. And the black pattern, if you were to draw a picture of over time, it would look like those loops with nodes and antinodes that we saw in the previous slide. I'd like to draw your attention to the two pink arrows that are shown on the left-hand side of the screen. Those arrows reflect the movement of one particle in a wave. So the arrow on the left reflects the movement of one particle, and the arrow on the right reflects the movement of another particle within this standing wave. You'll notice that both particles hit their maximum point of their oscillation at the same time, and both particles hit the minimum point of their oscillation at the same time. Those particles are in phase. And the takeaway from that is that points that are separated by zero nodes in a standing wave are in phase. But we can take it even further. If we move the second particle along the standing wave formation slightly and separate the two particles with an even number of nodes, and you can see the red points are the nodes, so those two particles are now separated by two nodes, which means they're an even number of nodes apart. You can see that those particles are still in phase. So our more general concept here is that points that are separated by zero nodes or an even number of nodes are in phase. This is the kind of thing that they'll assess in perhaps the start of a paper 2 question or a multiple choice question. It's a little trick that is easy to remember and can gain you quite a lot of marks, and more importantly, rush you through that paper a bit quicker. You can see that that second particle has moved again, and that second particle is now one node away from the first particle. So the particles or the points are separated by one node. And can you see that the first particle on the left reaches a maximum at exactly the same time the particle on the right reaches a minimum? That means that these 2 points are exactly out of phase. They're out of phase by pi radians or 180 degrees. And the same can be said for particles further down that standing wave formation. We've moved that right-hand particle so it's now separated from the first particle by 3 nodes. And these nodes, of course, are the red dots. And you can see that the particles are still completely out of phase. So it's important to remember that if points on the standing wave are separated by 0 nodes or an even number of nodes, then they are in phase. And if the points are separated by 1 node or an odd number of nodes, then those particles are out of phase. Let's head to your revision note template, go to the other notes section and write down the conditions necessary for a standing wave to form. Then head to your common diagram section and draw a standing wave. Annotate that diagram with nodes, antinodes, and the idea of phase difference from the particles on either sides of the nodes. Then complete questions 1 and 2 in the C.4 knowledge questions that you'll find downloadable below this video. Standing wave patterns can be formed using sound waves, and you would find these standing wave patterns in something like a clarinet or a flute or a saxophone. A wind instrument relies on standing waves to make it work. Standing waves can also be found in physical waves. If you imagine the string of a guitar, then the string of a guitar works by the string being plucked and a standing wave being formed within that string. And there are 3 main conditions for strings and sound waves for creating sound. Those 3 conditions are having 2 fixed boundaries, 1 fixed boundary and 1 free boundary, and 2 free boundaries. Let's look at these 3 specific boundary conditions now and note that they all 3 apply to strings and pipes. So when you're watching this, think about, oh, this could be the inside of a clarinet. Oh, or this could be the string of a guitar. There are 3 scenarios that you should be familiar with that can create a standing wave. The first scenario is one where the standing wave has 2 fixed ends. And you could probably think of a guitar string as an example of this. A string that has 2 ends that are fixed to a certain point. The patterns that can be created with a standing wave with 2 fixed ends can be shown here. The first harmonic pattern that's formed is one where we have simply one big loop. And you can imagine that is the first half of a wavelength of the wave, and the second half, if it was longer, would go like that. Therefore, we know that the wavelength of this wave is equal to 2 times L, where this is L. The second harmonic is where we have one full wavelength within the length, and it doubles back on itself to form 2 antinodes. We can see that L, this yellow line here, is equal to 1 wavelength. The third harmonic is where we have 3 antinodes, and this length L is equal to 1 wavelength and a half. So it's equal to 3 over 2 wavelengths. And the fourth harmonic and so on, the fourth harmonic is where we have 4 antinodes, and you can see that there's 2 wavelengths here within that L. The wavelength is equal to 2L over 4, which is a half L. We can come up with a relationship here. We have lambda equals 2L over 1, lambda equals 2L over 2, lambda equals 2L over 3, lambda equals 2L over 4. So a relationship is formed where you can find the wavelength of a wave using the formula 2L, which is the length of the fixed between the fixed ends, over n, where n is the number of harmonic and also the number of antinodes. A real-life example of this is a guitar string. We talked about that earlier. A guitar string has a number of frequencies at which it will naturally vibrate. These natural frequencies are known as the harmonics of the string. The second scenario of standing wave that you need to be comfortable with is 1 fixed end here and 1 open end here. So the lengths as before. The patterns we can create. The first pattern looks like this. And we have 1 antinode and 1 node. This point here represents 1/4 of a wavelength. So the L is equal to 1/4 of a wavelength, so wavelength is equal to 4 times L. The next harmonic, which is known as the third harmonic, is where we have 3/4 of a wavelength within that L. So that gives us the lambda equals 4L over 3. And the fifth harmonic is where we have 5/4 of a wavelength within the L. So our lambda equals 4L over 5. We can take that relationship there and pop it into a more generalized equation where lambda is equal to 4L over n, where n is the number of harmonics and is only odd numbers. The final situation we have is where we have two open ends of standing waves, an open end here and an open end here. Our first harmonic is half a wavelength. Our second harmonic is a whole wavelength, and our third harmonic is 1.5 wavelengths. So our relationship is lambda equals 2L over n, where n is a number of harmonic, which is exactly the same formula as we had before with two fixed ends. So really there are only two formulas you have to learn. This one for two fixed ends and two open ends, and this one for one fixed end and one open end. Okay, head to your revision note template and draw the standing wave formations for all harmonics for the two closed ends, the one open, one closed end, and the two open ends. Now this is important. The data booklet doesn't give you those formulae that we've just derived for these three boundary conditions. So you need to write down those formulae and you need to put a star beside them because you need to memorise them. You don't need to memorise them, of course. I mean, you can work it out in the exam, but it's going to be much simpler for you if you've got a really good idea of what those formulae are and how the wavelength is related to the length of the system given. Once you've done that, complete questions 3 to 5 in C4 knowledge questions. Let's take standing waves and move on to the next concept within this topic, resonance. And to understand resonance fully, we need to go back to simple harmonic motion. Simple harmonic motion, of course, was when systems oscillated freely. And you can see that we have a mass on a spring system here. If we were to pull that ball and extend the spring and then allow it to oscillate freely, then what we find is that that oscillation follows the rules of simple harmonic motion, and in particular, it follows the defining equation of simple harmonic motion that I'm circling here. It was acceleration is equal to minus omega squared x, and omega squared was the angular frequency squared. And the angular frequency was given by this equation here, omega equals 2 pi f. And f within that equation is the natural frequency of oscillation. So when we're looking at SHM, that oscillation is not being driven. It's disturbed, and then it oscillates naturally at its natural frequency. I'll give you another example. This is the mass in the spring system, but vertically. This mass is oscillating at its natural frequency. It's been disturbed, and then it's left to oscillate. And again, it follows this defining equation of SHM, where the omega is given by f, that's the natural frequency. When you displace a pendulum bob and then allow it to oscillate as shown on screen, it oscillates with a natural frequency, f. And finally, we looked at the standing wave earlier in this topic, and the particles within, let me try and follow it, the particles within this standing wave oscillate around an equilibrium point, and they oscillate at a natural frequency, f. Of course, one more thing, if we're looking at the particle here in these red points in the nodes, there's no oscillations there, all right? So with standing waves, it's only the points around the nodes that oscillate with simple harmonic motion, but the main point I'm trying to make here is they do so at a natural frequency. They're not driven. And of course, that's where we get this lovely idea of playing guitar, and you can see that they've been displaced from their equilibrium position, and then they oscillate around an equilibrium point, or they oscillate while forming a standing wave. That oscillation is not driven after it's been plucked. Let's think about driving frequency now, because sometimes you can take an oscillation and drive it. What do I mean by that? Well, let's look at this pendulum system over here on the right-hand side. You can see up at the top that the oscillation is being driven. It's not being displaced and then left alone. It's actually being moved at a certain frequency. And the one on the left here, the one that I'm underlining, this frequency, the driving frequency, is 2/3 of the natural frequency. So if the natural frequency is 3, this has been driven at a frequency of 2 Hertz. And can you see that the amplitude of this oscillation is not very big? Right? Let's go to the middle one. And remember we said that the natural frequency was 3 Hertz. Well, this system is being driven at the natural frequency. It's been driven at 3 Hertz. And look at the amplitude of oscillation here. Woo! It's very different to the one that's just been driven by 2/3 of it. And finally, let's go to this final oscillation. It's been driven at 4/3 of the natural frequency. So it's been driven at 4 Hertz. And again, this amplitude of oscillation is not very big, right? So if you're driving an oscillation, the resulting amplitude of the oscillation must have something to do with the frequency it's been driven at. I just want to introduce a term here. It's called resonance, or resonating frequency. Because when you drive a system at the natural frequency, like this one here, the system is said to resonate. And this middle pendulum here is resonating, all right? That's because it's been driven at the natural frequency. Now, when is resonance bad? Woo! Have you ever heard this myth about an opera singer shattering a glass by singing a note? Well, that's actually true. If an opera singer can sing a very pure, exact note at the same frequency as the natural frequency of the glass, then what the opera singer is doing is it's driving the frequency of the glass at its natural frequency. And that causes resonance. That resonance causes a maximum amplitude of oscillation, and actually that maximum amplitude of oscillation causes the glass to shatter. So it's not a myth, it's true. But you have to be a very good opera singer to do it, because you have to produce a pure note of the exact frequency as the natural frequency. Another bad example of resonance that we saw in theme B was the greenhouse effect. What happens in the greenhouse effect is that infrared radiation is absorbed by a CO2 molecule, and the infrared radiation has exactly the same frequency as the natural frequency of that CO2 molecule. When that exact frequency drives the molecule, it causes the molecule to resonate at its natural frequency. And what causes that is for the molecule to then later release another infrared photon. Here's another bad example of resonance. Skyscrapers will have a natural frequency of oscillation. And sometimes when you have an earthquake, that earthquake might shake or drive the building at a frequency that's equal to the natural frequency of the building. And in which case, that driving frequency that's equal to the natural frequency causes resonance. And that resonance causes these buildings to sway back and forth. If that's the case, then the structural integrity of the building might become compromised and the building might collapse. So it's a structural engineer's job to make sure that the natural frequency of the skyscraper is not easily driven by an earthquake. One final example of bad resonance. You may have heard the story of Tacoma Narrows, and this is real-life footage of Tacoma Narrows back in 1940. Basically what happened was there was a very strong and consistent gust of wind, and that wind drove the bridge at its natural frequency, causing it to resonate and oscillate and twist uncontrollably to the point where this bridge actually in the end collapsed. Now for many, many years, this story was told that the Tacoma Narrows Bridge collapsed due to resonance. Unfortunately, the story is a complete myth, but it's still a good point to make when we're looking at resonance and an object being driven at its natural frequency. An example of good resonance is a quartz clock or a quartz watch. And the thing that resonates within this is the quartz crystal. Let me talk you through how this works. We have a battery, and that battery sends a small electrical pulse to the stepping motor. This stepping motor steps up the voltage of the pulse. The pulse is set to a very specific frequency. That pulse is set to 32,768 Hz. So every second, this stepping motor sends 32,768 Hz to the quartz crystal. Why that exact number? Well, that's the natural frequency of this quartz crystal. And if you drive a quartz crystal at its natural frequency, then it will resonate. And that resonating frequency and that resonance causes a microchip circuit to turn oscillations into regular electric pulses, which is 1 per second. And what we're looking at now is a resonance curve. You can see on the x-axis we have the driving frequency, and this dotted line here shows the natural frequency of any system, and the y-axis shows the amplitude of oscillation. This curve shows how the amplitude of oscillation changes as you change the frequency of the driving system. You can see that when the driving frequency is less than the natural frequency, then the amplitude of oscillations increases towards that natural frequency. When the driving system is equal to the natural frequency, then we have maximum amplitude of oscillation. As soon as we increase the driving frequency, you can see the amplitude rapidly drops off of the oscillation. Head to your revision note template, write down the conditions necessary for resonance to occur. And what I'm talking about with that is that the driving frequency must be equal to the natural frequency of the system. Then go to your common graph section and draw the graph of the driving frequency on the x-axis against the amplitude on the y-axis. Let's finish off this topic by looking at damping. What is damping? And there are 3 types of damping that I want to address in particular. So what is damping? Well, a system is damped when 2 conditions are met. 1, that a resistive force opposes the motion of the oscillation. And 2, the amplitude or the energy of the oscillation decreases with time. Let's explain that in a little bit more detail. Number 1, a resistive force opposes the motion of oscillation. Here's a real-life example of that. Previously, we looked at a mass oscillating on a spring, and we did so in air or a vacuum. If we take that mass and oscillate it within a beaker of water, then that viscous force of the water will oppose the motion of the oscillation at all points. And what we'll find is that that oscillation will gradually die off. So when we talk about the first condition for damping, that first condition was a resistive force opposes the motion of the oscillation. This liquid will oppose the force of the oscillation. The second point was that the amplitude decreases with time. If you were to take the undamped system, where it's doing so in a vacuum, then you'll notice that the amplitude of this mass on the spring remains consistent at all times. We have this beautiful sine wave. However, if you place a system into a viscous situation, or it's damped, then the amplitude will decrease over time, eventually coming down to the point where it stops oscillating. And this decrease in amplitude, and you can see the dotted line here, follows an exponential decay. So this dotted line, if you were to plot the equation of the line, would be an exponential decay. Obviously, if we had a very viscous liquid in here like honey, then this exponential decay would decay faster. If we used the damping material as just air rather than a vacuum, then this exponential decay would take longer to decay. It would be less severe. And that's where we move on to the concept of critical damping and overdamping. Critical damping is if the mass returns to the equilibrium position as quickly as possible without crossing it. So in this case, critical damping would simply be straight down to here, and it doesn't do any more of these oscillations. Overdamping is if the system tends towards the equilibrium position much more slowly. I'd like to head back to that idea of the resonance curve, because with damping, this resonance curve adds an extra element to it. When a damped oscillator is driven, the energy supplied by the driver is providing energy to the system, but damping is doing work against the system. So we have to take that into account. So I want you to consider a system where it's been driven at its natural frequency, so it should be resonating, but there's also a little bit of damping there. Then what that resonance curve would look like is similar to the one we saw earlier, a peak around about the natural frequency. However, if we take the same system and we drive at the natural frequency, but there's heavy damping involved, then the resonant frequency actually reduces. So if there's a system that's been driven with heavy damping, you can expect the resonant frequency of that system to reduce. So let's head to your revision note template and write down the two conditions that describe damping or are necessary for damping. Then draw the graph for the damping of a resonant system and show the effects of light damping and heavy damping, and then describe or define critical, light and overdamping. And great, we've got to the end of C4. Now time for you to go and practice all this knowledge in the art of past papers, and of course I encourage you now to go to step 2, activate the application. I'll see you there.